Let's continue. And now we get to a big idea in this part. Here, I will just take the integral that we need to do in either in the first order perturbation or in the variational calculation. In both techniques, we need to handle this particular integral related to the Coulomb repulsion between the two electrons. In this part, we would like to look into the physical picture of such a multiple integrals. There are 6 of them all together. Okay. Now, let me write it down in a symbolic way. That means I don't need a particular form. I just call this 1s. In our perturbation, we know this is hydrogen-like. We have a form. In the variational calculation, we have a form. We want to find the optimum Z. Okay, so here I just take this as some 1s single electron state. But notice that when we start, we already make an approximation. Okay, just to consolidate what we discussed. Because we are pretending the 2 electron wave function is or can be written as a product of single electron wave functions. Okay, so this is the form. 1 electron in 1s and the second electron also in 1s. In our mind, we already assume there exists something like a single electron state, even for helium atom. Okay, and that is our wish. Actually, we want to do that so that at the end we have the same picture from hydrogen all the way to uranium and beyond. Okay, but for heliums onwards, this is an approximation. You must keep that in mind. Now, our purpose is to analyze what is the physical picture emerging from this integral. So I first copy the integral out. We have 1 electron in 1s, another electron in 1s. So I put a star on the left-hand side, 2 body, 2 electron wave function, the same 2 electron wave function, ground state, okay? And then in between is our electron-electron Coulomb repulsion. We evaluate, integrate over everything, thereby we want to make an estimation of what this energy, electron-electron repulsive energy, potential energy is, okay? I give it a symbol. I call it a J, an energy, and I also like to label it 1s, 1s. For that, I mean, I have 2 electrons, 1 in 1s, another also in a 1s state. Although we may not know what is this 1s state, meaning what is this wave function, okay? What is the best choice of this wave function? We don't know, okay? Or we don't know yet, all right? Nonetheless, the form already suggests us that we can label this 1s, 1s. You may wonder what for. Now, later on, as Mr. Gu asked before the break, maybe in lithium, we have the following situation. We may need to consider 1 electron, R1 is in 1s, the other one is in 2s. And thereby I will have a 1s, 2s, and this form can be labeled by J1S2S, okay? But that is later. Don't worry about it now. Now, let's look at the picture. There are many ways to interpret it, but the whole thing is that this J has a classical physics interpretation. That's the most, well, that is the first take-home message. Now let me convince you that there is a classical physics interpretation. Now I can separate this E square into minus E times minus E because they come from two electrons interacting. Each electron has minus E, so I separate it as minus E and minus E. And then we make use of Born's interpretation, okay, of wave function. Born says the interpretation of wave function is attached to wave function square. So I see phi R1, okay, in 1s, the same state, R1 in 1s there. One star, one without the complex conjugate, perfect. It will give us this. Similarly for R2, also in 1s, okay? So it is okay to rewrite this as this times that, okay? So following me up to here, because some punchline will follow. All right, 行不行? Okay, now, Born says the following. The wave function square is the let me start again. The wave function R1, okay, square times this tiny volume element, dr1, okay, this tiny volume element, this times that is the probability of finding the electron labeled by R1 at the location R1, okay, in the volume element D3 R1. Okay, that is Born's interpretation of the wave function. Now, if I multiply by minus E, we can interpret it as when one electron is in 1s state, this whole combination, minus E, the wave function square D3 R1, is the tiny bit of charge locating at R1 inside a box of this volume. Okay, do you follow me? This is the charge density of the electron. This is the charge density of the electron. This is the probability density of the electron. Okay? So I have the charge density of electron 1, I have the charge density of electron 2. Okay, a bit here, and then the Coulomb repel. So I have Q1 times Q2 divided by 4 pi epsilon, the distance. Okay, so this is an electromagnetic interpretation of the integrand. Do you follow me? Okay, so now that's what I meant by there is a classical physics interpretation for this term. Okay, it's like E and M, but we are mixing in some quantum concept. The wave function square is a probability density for finding the electron. Multiplying minus E becomes I find that much of charge of the electron here, there, they repel. the total Coulomb repulsive energy is to add up where the two electrons are. So I have this double integral over all the places electron 1 and electron 2 can be. Okay, so it seems to be rather ordinary, right? If you think about it. Okay, it's a good mixture of quantum mechanics and then your E&M knowledge. Okay, so here I try to draw some picture of this idea. So I have a nucleus here. If I only look at one of the two terms, I have this, okay? It means electron 1 who lives in this particular 1s state, although I don't know the form, but I know there's a wave function 1s, I want there exists something like that. So if it is existing in 1s electron 1, its charge is distributed according to the wave function square. It is the patch, this shaded region I try to depict. And that particular term in the integrand means the following. Electron 1 is at here in that box with the probability, the wave function square times the size of the box. If you multiply by minus E in front, this is the charge density of this tiny bit of charge belonging to electron 1. If you integrate over all this, that will give you minus E, because this wave function is normalized. Okay? Similarly, electron 2 has the same behavior. Notice that it is not two atoms, it is the same nucleus, but I don't want to overlap the picture, that will be too complicated. All right? Now the integrand is something like this. Bit by bit of charge from electron 1 and electron 2, they interact. So this bit times the other bit, that will be Q1 times Q2 divided by the distance, that will be a particular patch here and interacting with a patch of electron 1. Okay, the energy, interaction energy total, have to account for electron 1 can be anywhere here and electron 2 can be anywhere. Thereby we integrate over electron 1, electron 2's possible positions. Therefore we have this J integral. Okay, so that is the interpretation. Okay, so everybody follow this interpretation. Before I introduce the name is nothing, but you know, understand the picture. Is that okay? And the answer is no. You integrate it over, you can get an answer. Well, we have shown that you can find an answer. Okay, so don't worry about that. We have done similar thing before. You know, that is the same integral. When we plug in a hydrogen-like form, we can get this. Okay, it does not blow up. Okay. Everybody follow it up to here? Is that okay? So now, let me make some remarks. Up to this point, our interpretation actually does not depend on this form of the 1s state. Okay, because in principle, at this point, we don't know what this 1s state really is. Okay, we have tried the unperturbed one. It works, but not very good. We have tried variational. At the end, it has a funny Z charge. Okay, maybe there is even a better child wave function. We don't know. But our interpretation our interpretation doesn't need an explicit form. Okay, so that's the point number one. So it works for any state, actually. And therefore, later on, as I already hinted at, we need not consider the two states to be the same. Here, for helium ground state, we have the same 1s. More generally, we could have electron 1 in a state called phi A, electron 2 in a state called phi B. We have the same physical interpretation. The point is there is a classical E&M interpretation for this integral. So now it's time to introduce the name. There are many names for this integral. It is called the Coulomb integral, naturally, because it comes from the Coulomb. But more explicitly, it is called the direct Coulomb integral. Okay? That implicitly also means there may be something called the indirect Coulomb integral. I will show you a little bit later what is an indirect Coulomb integral. Okay, the key point is that the direct Coulomb integral here has classical physics E&M interpretation. And it also means the other called indirect Coulomb integral does not have classical E&M interpretation, but it is there in many quantum treatment of atoms. We will see that later, okay? But at this point, helium ground state, we only see this direct Coulomb integral. Another name for this, it is the Hartree energy, or Hartree term. Okay, but that is just a name. Don't worry about it, because Hartree was the first person to handle such term in quantum mechanics of atoms. So now I show you what is the indirect Coulomb term. Right? So let's look at the direct term one more time. The reason that we have classical E&M interpretation is that one electron, say R1, represented by where it is R1. On the left-hand side, it's in A state. On the right-hand side, it's also in A state. So you can combine this one and that one and form the magnitude square where the Born's interpretation comes in. And using that, you have the classical E&M interpretation. Okay? That is why the direct Coulomb term has classical physics interpretation. Okay, follow me? Now look at it one more time. Now, what if? Okay, follow me closely, please. What if on the right-hand side, this is not R1 but R2, and this is not R2 but R1? Okay, I have two electrons, R1 and R2, right? Two positions. What if this one is R2, that one is R1? Okay, now this is what I just wrote here. I have the same, I should put another integral. I mean to integrate over all the 6 coordinates, okay? Now look at this integral. I do not find any psi star psi of the same coordinates. Thereby, I do not have psi square for which I can interpret as a probability density. All right? So this looks very much like the J integral. Nonetheless, there is no classical physics interpretation. This is called the indirect Coulomb integral, or it is called the exchange energy, or it is called the Hartree-Fock term, or the Fock term. After another person, okay? So we do not see this term in helium ground state because in our mind, helium ground state, both electrons are in the same 1s state. Therefore, no matter when A equals B, we are guaranteed to see this classical interpretation, okay? However, as we just mentioned a while ago, we may have one electron in 1s and another electron in 2s. We do have A, B, different state. When we have two different states with two electrons, it is possible to have both the direct integral and the indirect Coulomb integral. Okay? Do you follow me up to here? Okay? Any questions? You mean say it again? Okay. Now what I'm saying is that for the helium ground state problem, we only see this kind of integral. Because in our mind, we have A being 1s and B being 1s. In our mind, ground state helium is 2 electrons in 1s, and then the spin part will take care of the Pauli exclusion principle. Okay? Is that okay? But we want to anticipate something for other atoms, not only helium ground state. For example, how about helium excited state? In our mind, there will be one electron in 1s, another electron in 2s. Okay, do you follow me? Therefore, we do have a situation where A state is different from B state. Okay? Then in such a situation, when we handle the Coulomb term, we will encounter two different kinds of integrals. The first one is nice. 1s, 2s, 1s, 2s, and then we can still interpret it classically. What I'm anticipating or advertising is that when we have two different states, A and B, there is another type of more troublesome integral that we need to handle, in which we have electron 1 in A on the left-hand side, but electron 1 in B on the right-hand side. It looks as if on the two sides of the integral, the two electrons has been exchanged position. Okay? Then, at this point, I just would like to introduce the following possibility. First, we will see this term in helium excited state, in lithium atom ground state, because we will have to deal with 3 electrons, 1s, 1s, 2s. So there will be 2 different states involved. Okay? And then there will be this term in many other atoms. Okay? And second point is that this K integral does not have classical interpretation. Okay, so that is the point I would like to introduce about K at this point. Okay, is Hartree energy the electron interacting with itself? No, no, it is handling in an average way what the second electron is interacting with one electron. Basically, it is this. Okay, it has to do with two electrons. Choi, because I have a 6, I integrate over two electrons positions. Okay. You may be worrying about a little bit, just like the other students. Do we include something like an electron interacting with itself? Okay, now that is a very advanced question. I don't want to say anything at this point, all right? Okay, but the big picture, it has to do with electron 1 interacting with electron 2. Okay, so now that is the interpretation. Okay, now let me introduce the big idea following this interpretation. Now I go back to the first equation, the J1s1s, and now I rewrite it in a different form. I collect the terms. So I'm here. Okay, I'm here. All right. Now I collect the R2, the second electron term, the integration, the denominator, and integration over R2, and put it in the middle. Okay, so okay, so do you understand what I did here? I collect all the things about R2, including the integration, and then put it in the middle. All right. And then if I also put this minus E into this minus E, and therefore I have a plus E squared and this. Okay. Okay, so now let us focus on this line, this particular line. Okay, it is very suggestive. Okay, or it is implying something very important. Now, first of all, this is a function of R1. I mean, after you do this integral, you integrate over R2. What is left is R1. Okay, do you understand what I'm saying? So this whole integral at the end is an integral which is a function of R1. Get me? Okay. And now we can interpret this classically as well. At this point, I'm looking at only this sphere, this mirror out of electron 2. So I'm thinking about a particular position R1 here, okay? I don't change R1, I don't integrate R1 first. And then I ask, now this bit will be providing a Coulomb potential energy at this point. The other bit will also contribute a Coulomb potential energy at the same point R1. I add up all the contribution due to R2, the second electron, thereby I know what is the contribution of the second electron at a particular point of the position of the first electron R1, okay? And that is this thing in the middle. Okay, and therefore, we can represent this as an effective potential due to R2 at the position of R1. Okay, this is one important step forward. Is that okay? Do you follow? You follow? Now, what's more, if at this point, look at this thing. It looks like an operator in a Hamiltonian, do you see? And now, if I know what this 1s state is, it is like an expectation value of this particular way of handling Coulomb repulsion between electrons, right? So this is how electron 2 affect electron 1. I take this, I can reduce the 2 electron problem into an effective 1 electron problem. Okay, so let me show you how. With this idea, all of a sudden, it hints at the following equation to solve for the ground state 1s state of helium atom. We have electron 1 kinetic energy. We have electron 1 seeing the nucleus. Okay, so these two terms, no problem. But after much work interpreting how we calculate the Coulomb repulsive energy, at the end, it looks as if, given that electron 2 is in this state, 1s state, it will contribute a effective potential on the electron that I am focusing on. Okay, so I will take this integral. This is a function of electron 1. Okay, so this is the term that in the middle, I integrate over the second electron. Now I call R prime. Okay, more generally. So that will be an operator which is a function of R. Okay, and now I have an effective single electron state Schrödinger equation. Okay, so now this equation really works some Nobel Prizes already. Okay, but at this point, I would like you to at least stretch your mind and try to understand why we can write down something like this. Okay, this term effectively take into account how the other electron is affecting the one that I'm focusing on. Okay, do you understand what's being done? Hello, hello. Okay. Now, what's being done here is very profound, very important in physics. At this point, we have reduced the 2 electron problem into 1 electron problem. Okay, now that is our goal. This is what we want to do, and we find a way to do it. Okay, so do you understand this point? 行不行? Okay? But don't be too happy. We have reduced it to single electron problem, but we have also revealed, okay? We have also revealed or unveiled the complexity of many electron problems. Okay? Now let me explain. It looks as if it is a Hamiltonian acting on the unknown that we want to find what is the 1s state. If we can solve this, it will give us the 1s state, the wave function, and the 1s state energy. Okay, that looks okay, quite nice. However, when you have electron-electron interaction, it always comes out with the following complexity. 呢個複雜性，複雜性. Now, this is the one that we want to solve, the ground state single electron state of helium, okay, 1s state. However, the new term that represents how the second electron also in this 1s state will affect this first electron also depend on the unknown 1s state. Okay, do you see that? The potential, the extra potential term needs your answer. Wow, that's rather funny, right? This is an equation to solve for phi 1s and epsilon 1s. Yet, in order to have the equation, the operator part, you need the solution. Okay? Now now is the punchline, okay? The punchline is self-consistent. When you solve many electron problems, there is always a need to do self-consistent solution. What do you mean by that? You may make a first educated guess for a good 1s state for helium. For example, you take the hydrogen-like, the unperturbed one, okay? You put it here. Probably you should put in some parameter to adjust, okay? You assume something, you plug into here. Therefore, you can create this operator. Thereby, you have this part. You write a software so that it will give you out as an output a new phi 1s and some energy, of course. You compare the output with what you put in as the input. If they differ by your tolerance level, you tune your 1s state again, plug it into here, recalculate this potential term, create this, construct this operator, solve the solution again, compare result, adjust it, do it again and again until consistency, until convergence. Okay, so do you understand? I mean, understand the concept. I'm not going to ask you to do this in our course, but that is the beginning of many, many research problems and advanced level topics. I want you to understand, to realize this idea and concept, okay? Do you get that? You get that? Okay? All right. Now, let me tell you something even worse. when you have two different states. Okay, let me tell you the answer. Okay, now, so someone has done this for helium atom ground state, do convergence, try the very best. Okay, the best physicist, the best computer you have. The answer is, after you do that, the 1s eigenstate is this, but that's not the end of the story, because that means you also know phi 1s. Then you construct phi 1s R1, phi 1s R2, and go back to the helium Hamiltonian, look for the expectation value. That will be your energy. The energy is this number. Okay? In EV is this. Okay? It is closer than the variational calculation and the first order perturbation. Yet, it is not equal to the best known experimental or exact value. It's still off, okay? And if we extend, when A and B can be of different states, there are complications. Now, first of all, this you will not only get one single equation. You will have coupled equations. Okay, for example, phi 1s and phi 2s. Okay, you can imagine if I have two electrons, one in 1s, one in 2s, right? So when I solve for 1s, the other one will be in 2s. When I solve for 2s, the other one will be in 1s. I will have two, not only one equation, but two equations. But both depend on the solutions. So you have to make two guesses. Then you construct the operator for the two equations. You get two outputs. You compare the two inputs with the two outputs, you get convergence. Follow me? Do you follow me? So the bigger atoms you have, the more equation, the set of equations is bigger, more complicated. Of course, you have more electrons, right? Okay. So that is the complication number one. Actually, there's another complication number two, okay? When you have electrons in 1s and 2s, this term will come in. This is the energy. Part of this integral, I have two integrals, okay? Part of the integral will give you an extra term in this Hamiltonian. That is the exchange term. Therefore, you will have a more complicated set of equations. Nonetheless, the concept remains the same. We will need to do self-consistent calculations, okay? But don't worry. If some of you become interested in this exercise, one place to look up in the technical path is an undergraduate textbook on computational physics by Kunin, the Caltech professor, okay? And then you can find a program in chapter 3 that gives you the method to do helium ground state. So this is the problem that we just described, okay? If you can't imagine how one can do that, you look up this book. In the appendix, there is a sample program. Then you can realize how to do iteration to convergence, okay? So this, I hope to give you some idea. At the end, although our discussion is only on helium atom, I hope that you have a sense now, at the end, even for bigger atoms, it is possible to construct an effective potential due to n-1 electrons acting on 1 electrons, and then we have an effective single electron equation to solve for the different states, 1s, 2s, 2p, 3s, those states for an atom. And only after that, you can exercise the Pauli exclusion principle to fill the electrons in, okay? So I hope today I have explained to you some of the mystery that you have heard over the years, okay? From chemistry course, you take it for granted that a potassium atom will have 1s, 2s, 2p, 3s, 3p, and 3d and 4s, okay? So it seems to be it's natural. What I want to tell you is that it's not so natural. There is a lot of work within the quantum mechanics framework, and also very clever approximations. You may say very dirty approximations, but in my opinion, very clever approximations to handle, I would say, 95% or so of the Coulomb repulsion between the electrons, so as to reduce it into an effective single electron problem through which we can retain the nice feature in the hydrogen atom states, so that we can fill the electrons in and explain the periodic table successfully. Maybe nature really works approximately like that. You see? Okay? The fact is that 92 elements or 120 elements can be explained in this approximated way. Okay? So I have to stop here today. Next time, there's an appendix. We discuss a little bit more about this scheme, and then we will discuss how we can have the periodic table. The second part of this part of other atoms has to do with what is the rule to fill in electrons. Of course, you know the rule, Pauli exclusion principle. But the main point in our discussion is that, is there anything more general than the Pauli exclusion principle? The answer is yes. There is an anti-symmetry requirement of many electron wave function. And we will introduce that, and at the end, we understand why there is a Pauli exclusion principle and why we have the periodic table. And then we will move on to molecules, okay? So, so long for now. I see you next Tuesday.